Let's do a calculation involving work, heat, and energy. I'm going to take an ideal gas and expose it to a 100-watt heater for 10 minutes. So that's going to heat the gas up, but at the same time, I'll allow the gas to expand from 2 liters to 10 liters against the atmosphere. So what's going to happen to the internal energy of that gas? Well, we have a new unit here, watts, and that's a unit of power. How much energy is transferred per second? How many joules of heat per second are transferred? So a 100-watt heater can transfer 100 joules of heat to a system for every second. So it's going to operate for 10 minutes while the system does work. So let's look at the heat transfer first. The energy change will be the heat plus the work. The heat transfer is that 100 joules per second of the heater working times the 10 minutes that it works, and I have to change those minutes to seconds, so 60 seconds per minute, and that gives me units of joules. 60,000 joules are transferred by that heater. Now, the system's also doing work. The question is, did I use all those 60,000 joules to do work, or did I use fewer or more than 60,000 joules of work? If I use exactly 60,000 joules to do the work, then my temperature won't change. I'll absorb 60,000 joules and do 60,000 joules of work. So it's interesting to see, did the temperature change? Did the energy go up or down for this system? The work will tell us. The work is the external pressure times the change in volume with a minus sign. So the external pressure, 0.978 atmospheres, minus, and the change in volume. Change in volume is always final minus initial. Final volume 10 liters, initial volume 2 liters, change in volume 8 liters. So I can do that math, minus 7.82 liter atmospheres of work. And here now I have a problem. My heat I calculated in joules, but my work I calculated in liter atmospheres. Liter atmospheres is a totally fine unit of energy. They're just not the same, so I have to change one to the other. So let's change liter atmospheres to joules. And I never remember what the conversion factor is, but I do remember the two gas constants. I know one in joules, 8.314, and one in liter atmospheres, 0.082. So the ratio of those will change liter atmospheres to joules. So I can take my 60,000 joules of heat, my 7.82 liter atmospheres of work, convert that to joules by just multiplying by the ratio of the two gas constants. I'll take 8.314 joules per mole Kelvin and 0.08205 liter atmospheres per mole Kelvin. All those units cancel except the joules. And that gives me, you notice, factor of about 100 there. So about 800 joules of work are done by the system. So it does about 800 joules of work, but absorbs 60,000 joules from the heater. So clearly its internal energy is going to go way up. Its internal energy is going to go up by the difference, heat plus the work, and in this case the work is negative. So it's the heat I absorbed minus the work I did, or an internal energy change of 59,210 joules. So this is a process involving both heat and work for an ideal gas, but we can track them with the first law of thermodynamics.